Now there is a theorem. If f and g are function of bounded variation on closed interval a comma b, then their sum f plus g, product fg, and difference f minus g are function of bounded variation on closed interval a comma b. इसका प्रूफ देखते हैं. लेट p is equal to x0 is equal to a comma x1 comma so on xn is equal to b be any partition of closed interval a comma b. We have summation mod del mod delta f plus g r mod is equal to summation mod f plus g x r minus f plus z x r minus 1, which is equal to summation mod f x r plus g x r minus f x r minus 1 minus g x r minus 1. Now, which is equal to summation mod f x r minus f x r minus 1 plus g x r minus g x r minus 1, which is equal to summation mod delta f x r plus delta g x r, which is less than. Now it is greater than equal to summation mod delta fxr plus summation mod delta gxr, which is greater than equal to vf plus vg, which is equation number 1. Since the inequality 1 holds for any partition P, on taking supremum, we get V f plus g is less than equal to Vf plus Vg is less than infinity. Since f and g are of bounded variation, f and g are function of bounded variation, it follows that f plus g is bounded variation. This proves the first result. Now since f comma g are of bounded variation on closed interval a comma b, then there exist positive number capital M and capital N such that mod fx is less than equal to m and mod gx is less than equal to n for all x belongs to a comma b, which is equation number 2. If we get h is equal to fg, then delta hr is equal to fg xr minus fg xr minus 1, which is equal to fxr gxr minus fxr minus 1 gxr minus 1, which is equal to fxr gxr minus gxr minus 1 plus gxr minus 1 fxr minus fxr minus 1, which is equal to fxr delta gr plus gxr minus 1 delta fr. It follows that summation mod delta hr is equal to summation mod fxr delta gr plus g x r minus 1 delta fr, which is greater than equal to. Now summation mod delta hr is less than equal to summation mod fxr mod delta gr plus summation mod gxr minus 1 mod delta fr, which is now it is greater than equal to m summation mod delta gr plus n summation mod delta fr by equation number 2. Now it is greater than equal to m vg plus n vf. Hence vfg is less than equal to m vg plus n vf is less than infinity. Since m comma n are finite and f comma g of bounded variation. Consequently, f g is also of bounded variation. This complete the proof of theorem. Now summation mode f plus g x r minus f plus g x r minus 1 is equal to summation mode f x r plus g x r minus f x r minus 1 plus g x r minus 1, which is equal to summation mode f x r minus f x r minus 1 plus g x r minus g x r minus 1, which is greater than equal to summation mode f x r minus f x r minus 1 plus summation mode g x r minus g x r minus 1, which is greater than equal to v f a comma b plus v g such that a comma b. Then v f comma g, v f plus g a comma b is less than equal to v f a comma b plus v g comma a comma b. Hence f plus g is bounded. Now summation mode f minus g x r minus f minus g x r minus 1 is equal to summation mode f x r minus g x r minus f x r minus 1 minus g x r minus 1, which is equal to summation mode f x r minus f x r minus 1 minus g x r plus g x r minus 1, which is less than equal to. Now this function is less than equal to summation mode f x r minus f x r minus 1 minus summation mode gxr minus gxr minus 1. Now this function summation mode f minus gxr minus f minus gxr minus 1 is less than equal to v f comma a comma b minus v g comma a comma b. Then v f minus g a comma b is less than equal to v f comma a comma b minus v g comma a comma b. Hence f minus g is bounded. So we prove f minus g is bounded, then f plus g is bounded, and f comma g is bounded. And that's what we need to prove, that f and g are function of bounded variation. So their sum, product and difference are function of bounded variation on a comma b.